Hello friends, I'm hoping that all of you are very secure at your home and following all the instructions from government of India to safeguard yourself and your family from the corona. Okay? So let's start this machine learning lecture on TutorASRumale. Advances in machine learning. We are going to see reinforcement learning. So if you see what is the reinforcement learning, you'll find that reinforcement learning is something which we require to consider as the learning which is very advanced in machine learning. Okay, because it is unsupervised and reinforcement is what you are actually trying to learn. What you can say out of your experiences, just like a human being. And for having such an algorithm in the machine is quite difficult to implement. So this is an advances or advanced type of machine learning. So let's go. We are going to see here the introduction, then elements of reinforcement learning, then model-based learning, your value iteration and policy iteration. We are going to see. So let's see what is the definition of the reinforcement learning. So as per the book definition, if you go with this as a reinforcement learning, we say that is in reinforcement learning, the learner is a decision-making agent that takes action in an environment and receives a reward or penalty for its actions in trying to solve a problem. So if you see what is there, it's a decision-making agent. What's a learner? Here, learner is a decision-making agent. Okay, learner is a decision making agent. There is no one to guide the learner. Okay, and how it's make the decision actions in an environment. Okay, and these decisions are made based on the reward or penalty for its actions. Okay, so learner is making a decision. Let's say a simple example: a small child, when no one is at home, try to touch something. Let's say suppose you just have a candle there, and the child get fascinated by the candle light, and so it's just go to the candle and try to touch the fire. What will happen? The fire will burn its skin, and it will learn from that experience that it is a dangerous thing to touch a burning candle, okay, or lit up candle. So that is what you can say learning from the penalty. No one is there to guide you. The situation and the entire environment is new to you, and whatever the happenings are there, you are registering those. So you are having a particular memory in your thing. So if you go with this, you know that here in machine learning, when we are using the reinforcement learning, you have if you are using the reinforcement learning, it's a set of trial and errors. Okay, so after a set of trial and errors, that machine comes to know that a particular action causes particular type of result. Every time an action takes place, the machine also registered the output of that action and the reward. Okay, so that gives thing, and so the machine should learn what called as the best policy to carry out that particular action. So this best policy is what? To maximize the total reward. When we say this maximize the total reward, we are talking about the positive rewards, okay, and not the punishment. Reward are always of two types. That is, either you can gain from the situation or you can lose to the situation. For example, let's say suppose you are having a robot, okay, and this robot require so you program this robot, and this robot required to pick something. Okay, so you have a robot to this robot, and this robot arm try to pick something. So whenever it try to pick something heavier, okay, than its capacity, it won't get it can say the lifting possible. So after trial and error, the robot will automatically what can say guess that a particular type size and particular weight is what it can pick up from using its robot arm, and that is what you can say the policy. Now, the maximized total reward means the base policy is that to pick up the optimal weight of the particular thing, and that robot can do this. So when robot start picking up the like that, the robot arm lasts for a longer time. So if you see this definition, once again I'm repeating, it's a reinforcement learning. The learner is a decision making agent, okay, and it takes actions, environment, receives reward or penalty for its action in trying to solve a problem. After a set of trial and error runs, should learn the best policy, which is the sequence of actions that maximize the total reward. Okay, this is a simple definition for reinforcement learning. Let's know what the reinforcement learning. Let's consider this example. Now, let's say suppose if you want to build a machine that learns to play chess. Okay, it's obviously a chess is having 8 by 8 mattress. You are in total 64 houses, and every player is having total 16. What do you say? Uh, chessboard players. Okay, pawns, horse, camel, horse, this elephant, uh, and then you are having a king and queen, and everyone is having a different type of rules and action. So there are too many possibilities. If you go with the possibilities of moves of everyone, they may be around 64 factorial, something like that. So it's quite difficult to have a supervisor there who can guide you through each and every move. Okay, it's not possible. For example, like right now, let's say suppose when we learn anything in our schools, what our teacher actually taught us at a primary level, 0 to 9. Okay, then A to Z, few words, and likewise, and how to form the sentence. A basic structure is taught to us, but afterwards we are forming different structures. For example, right now I'm communicating with you, whatever sentences I'm using. Okay, those sentences are not taught by my teacher. Teacher only taught me how to form the sentence. Okay, but if a teacher decide to taught you the every sentence possible using a language, impossible. It is simply impossible. Okay. So in same way, again, let's say suppose you want a robot to play, just not chess. You want to a robot which can play a football or any other game. It is impossible to have a supervisor who can teach or who can guide that particular machine through all the moves. Okay. So machine have to learn each and every moves on its own. So it is very costly to have a supervisor. There are these reasons. First reason is that it's very costly to have a supervisor. Okay. So in such cases, when we are on the game theory or something, another thing is that these cases there is no such thing as the best move. Okay. So uh, you if you see this, there is literally no such thing as a best move in any game. Okay, because it's totally depend upon how competent is your opponent. When you are having a game, your move, whether it is the best or not, totally depend upon how competent is your opponent. And so there is no such thing as a best move. So it's totally depend upon the intelligence of the other side or other person or other participant who is actually playing with you. And so this is the thing. So where the supervisor fails. So what you have to do here? The reward here is winning the game. This is the final reward. So how you can win the game? Let's say suppose if you sum up the thing, okay, if you sum up all the things, you can say if you win at every move, you can say your final reward is winning. Or you can go with the probability that if your 51% of moves or the moves greater than 50% are positive at a winning side, then you win the game. So if you go with the logistic expression, you can simply see this thing. So if you go with this is a probabilistic method. Okay. So here you have to register the reward of the winning and you have to register the reward of losing, and then based on that particular move in a particular situation, and likewise you have to register these. So what model actually or program you are having, a program which actually registered all these moves. Okay, so here if you see this, you'll find this thing. So reward is always the outcome of different set of moves. Okay, for different instance of game, and it's not always necessary to won each and every move. It's maybe okay. It's not always necessary to have always the positive reward to win a game. If you consider the 50-50 as the thing to draw the game, then the whoever wants 51% is the winner. Okay, so you can 49% of time you can make the mistakes, but still you are winning the game. But that winning is not called as a winning. This simply called as saving yourself from the losing. So what is the best possibility? You have to win 100% of time. So the machine learning, if when the machine goes on playing the game continuously, maybe for first it win 51% of the moves. Maybe for the next play it go on increasing and go to around to 70%, and likewise. And once a time come when machine knows each and every move possibilities, and likewise, and then machine can win almost each and every game. That's what happened with the uh, uh, this chess game in artificial intelligence. Okay, so this is what we are saying. Now, this is what the elements of the reinforcement learning. Here, here having a simple environment. Environment means the real life situation in which you are giving this environment changes, and then you are having an agent, or what you can say the learner, the agent. What agent does? Agent try to take certain action. Okay. This agent actually try to do certain action. These certain actions taken by this agent, okay, into the environment, either gives is the reward, or it gives it the negative reward, what we call as the penalty. So the penalty means this negative reward means your agent is at loss. Now, from this reward, when this reward is there, agent actually changes its state. Okay, because whenever an agent take an action, agent's state get changed. Okay, in that environment, and a reward get registered. And for this reward, so agent know that is due to this particular action, he got the failure and it's changed the state to the negative direction. Due to this, it's get the positive and it changes state into the positive direction. And all these things are stored somewhere. So you can say you are having a lookup table here. Okay, so this table are just like this. You can say this action consider, let's say it denotes the action. Okay, and you are having the positive reward. For positive reward means the reward which gives you the winning, and then you are having the negative rewards, the rewards which are not giving you the winning. And let's say suppose you have taken certain actions, one or three actions here, all these get registered. So you know that is you are saying move one. Let's say this move one is the label given to this move, not the sequence number, and it gives you the positive reward. Let's say you made the move two. Okay, move to give you the negative reward. Then you made the third move of type move one. Okay, so of type move one, let's call these as the ones variation, so call these as the one dash, and it gives the positive move. So next time when this agent want to progress in the situation, it's know that to have the proper output, it must have to have the variation of the move of type 1, so that it can always get the positive result, and instead of losing it can win the game, or it can gain from that particular experience. So this is what we call as a reinforcement learning. Okay, this is what the reinforcement learning. Everything is registered into the memory of the agent. Okay, but if you keep on registering in this memory continuously, what will happen? The agent will become intelligent. This is how we learn. We born, yeah, at the birth time. Okay, we don't know anything, so we keep look observing the things. Okay, and we keep observing a thing. We keep trial and error methods for standing, doing, eating, everything, and we registered every our good and bad experiences, what we call as a reward. And from that, now we know which is edible and which is not edible. Okay, many of us have this experience that a small child generally see anything and try to taste anything. Means whatever they get in their hand, they try to put those things in their mouth. Many times they put the cockroaches also in their mouth. Yeah? But as soon as they say that this is an insect, they know that it's not thing to throw it away. And so that is what how our brain actually learns. Okay, so this is the reinforcement learning. This is the way human beings, or this is the way many living beings actually learn from the situation. And so this is a simple model of the reinforcement learning. So if you see the elements of reinforcement learning, you are in the agent as a there, reward is there, action is there, state is there, environment is there. The one element not shown in this diagram is the policy which is made based on these experiences which is made by this agent itself. Okay, so let's think. So now there is a basic mathematical model given by this Markov decision model. This is an episodic model which is considered a discrete time. Okay, where it says that, okay, if S of t, which belongs to state S, denotes the state of agent at time t, where S is say all possible states and t is the discrete time. So t is 0, 1, 2, and likewise. It's a discrete time. Okay. S is the superset of these all states possible. So you are having this st to S denote the state of agent at time t. So st is what? St is the state of agent at time t. Okay, and state of S is the state of all possible states. Okay, in a discrete time. So if such thing are there, you have the action 80, which belongs to a set of all actions possible at a particular type of state. So you can say that is action 80, which belongs to set of all actions possible agent states at time t, and is a set of all actions at the this state st. This is the another thing. Now the next month says that there is a reward whenever this agent is in a state st. Okay, and it takes the action 80. Whenever this agent, okay, if the agent is in st and if there exists an action 80, okay, there also exists a reward rt plus 1, which belongs to all type of rewards possible which are received. Now, why this is t plus 1? Okay, because this reward actually helps the agent to move to the next stage st plus 1. Okay, and that's why we see T1. So if when you have this type of reward, okay, this reward and the next state are sampled from their respective probability distribution. So we can say the probability of these rewards. We can simply see this probability, that probability of RT plus 1 is such that there have to be ST and AT. Okay, so this RT plus 1 may be the positive, or this RT plus 1 may be negative, and probability of movement of this agent into the next state is again depend upon the its present state and present action likewise. So these are the two probabilities that we are having. So if you see this Markov decision model, the sequence episode of actions from the start to the terminal state is an episode or a trial. So let's take the one state, and for that particular state you are having the state, and likewise based on the particular action and so on. So here the agent required to make the policy. So let's say that is this pi defines the agent's behavior, okay, and its mapping is okay, it's a mapping on state environment actions such that this pi means a state which directs to the particular action. So the policy defines the action to be taken in any state. So this st, okay, such that AT is equal to pi of ST. So when you say pi of ST, its output is the and the value of this policy pi is given by uh, V raised to power this pi of ST. It's an expected cumulative reward, or what can be the value that will be received while the agent follows the policy. And the starting state, we are not saying S0 as the starting state. Instead, we are saying ST as the starting thing, because we don't know at which time exactly the agent start moving the thing. So if you see all this resembles Markov decision model, resembles the reinforcement learning. Markov decision model resembles the reinforcement learning there, and so it is the base model used for the reinforcement learning and can be used in a very efficient way. And this is a base model for reinforcement learning right now. So there are two type of Markov decision model or the episodic model. Why it is episodic? Because it's goes step by step. So it's required to have the episode of every step. So to have the maximum expected reward, when we say maximum expected reward, that means you have to win at least 51 time, at least 51% time. Okay. So here the value, this value v raised to power pi of st should have to be such that estimated must have to be such that you have to get all the rewards rt1 plus r of t plus 2, then rt of this capital T must have to equal to this estimation of summation of I equals to 1 to t, where you know that t is the set of discrete time t second 0, 1, 2, 3, 4, likewise in each time, and here you are having the reward at each time. So this a of st, this value must have to be positive in finite horizon. Why it's called as this finite horizon or of the episodic model? Because here you are having 1 to t, that a time you know when this time is going to finish. Okay, for example, let's say suppose you want to make some move. Okay, then to make this move you require to learn the things in a particular time itself. So agent tries to maximize the expected reward for the next t steps and likewise. So you may have the Markov decision model for the infinite thing. There are certain situations where you require to go in the infinite horizon model. Okay, so there is no sequence limit, but the future rewards are discounted. So you require to get the discounted. The process is a continuous process where the machinery need to learn everything. For example, let's say suppose you are having instrument, a machine, okay, who is actually trying to learn the seismic waves or the sea waves, so that it can predict whether there is a possibility of tsunami or not. And likewise, then this instrument, they have no horizontal, means time is infinite here. Okay, it's required to register these things, and based on this learning how to find out all those things, and right. So if you go with this t changes. If you see here, the t in the above equation changes to infinite. Okay, but infinite means you are having sync. Now here this lambda or y is required to be 0 and 1. Okay, or y equal to 0, the intermediate reward counts, and y approaches 1, the model becomes mature. So as you get this y's value increase, if this y is 0, immediate reward counts. Okay, y is 0 means that you are having the reward right now. But as y approaches 1, your model becomes more mature, and this mature model will give you maximum, what you can say, correctness. So y equal to 0 means you can say 51% winning, and y approaches to 1 means above 90% winning, like that. So as your model become more, it is using trial and error, it can start learning each and every moves in a sequence or in a linear fashion. It know that now this move can give the winning and everything into the program. Okay, so this is how we can go with the elements of reinforcement learning. And this is how Markov decision model can be used to give these elements of reinforcement learning and can be used for reinforcement learning. So next is the optimal policy. For every policy this part, there have to be some optimal policy values there. So when you get the results, because this value is either positive or negative. So optimal policy is the policy which gives us maximum positive values. So this optimal policy we are considering where maximum positive value we are getting as a V star of ST instead of saying V of ST. Okay, so for all states, okay, so maximum of this are used, and so if you see this, instead of working with values of state, we prefer here to work with the values of state action pairs. So if you say Q of ST and AT, that is for a particular state, there is a particular action which is giving you a positive or actually positive rewards. You can then call that value as the V star ST. You can include that into that V star ST. So this is what we can say. So there is an optimal policy for this Q star ST 80 as the value that is expected and cumulative reward of the activity taken. So this can be given like Q star ST equals to max of Q star ST and 80. Okay. So on solving this above, we get the Bellman's equation. Uh, Bellman's equations. So that is maximization. If you see this maximization, you can see this as a clear example of dynamic program. Okay, mean and max calculation using dynamic programming for this. So you get the clear example that you are getting the different outputs from the different state of action, and you are trying to find out the max action from this. So this is a Bellman's equation that we are getting using this thing, and this is what are elements for of the reinforcement learning in machine learning. Now let's see the next thing. So model based learning. So what is model based learning? Model based learning is one type of reinforcement learning. Okay. Here we are actually using in model based learning what we are using, that is parameters model. So we consider this probability of reward, and then we are considering the probability happening of the positive state due to the past action. So based on these two probabilities, we come up with this what we call say the optimal policy. So we have the optimal policy pi star ST, which give the argument positive arguments maximum, and you say this is according to things. So here you are considering this probability of state future state on the base state with the whatever value we are getting from this state, the optimal value. So whenever we get the optimal value, there is a guarantee that the next state will be giving us the positive reward. So here you are estimating this, and as this lambda or y, okay, approaches 1, okay, initially it is 0, and as we our model go on learning, it's a thing. So this thing, but the model based learning means what? Model based learning is something like you are given with a basic functionality first. So it's not you are not having the complete supervisor, completely active supervisor. Instead you are having a thing just like we learn A to Z in our primary state, and now we can create the sentences, we can write the books, research papers, and likewise. So what that model based learning, we learn a model and now we are using that model, and based on that model we are increasing our lambda, because this increase lambda increasing is only going to give us what you can say the maximum output positively. So in the same way, when we have this reinforcement learning implemented on model based learning, we are actually giving these things. So here model based learning, because everything is known, we know the number system, completely know the environment model parameters. Number system, how many numbers are there? 1 to 9 are numbers. 0 is not considered as a number in number system, but let's consider 0 to 9. Now you know these 10 numbers, decimal system, and you can build any number from this 0, 1, 2, 3, 4, 5 to 9 are there, but you can build now 10, 11, 999, 9 lakh and 99 and likewise. Okay, so if you know the environment model parameters completely, that is, you know the first thing, what you get, you can directly solve the things using dynamic programming. I already bold out this in my presentation, but think. Okay, so reinforcement learning actually help us. Model-based reinforcement learning help us in the what we can say to learn things very what we can say efficiently than without the model. Without model, it requires some time, but as soon as you start registering the state and the rewards and action relationship and map, and it's come up with the policy, and then policy get optimized, you know that model is created, and afterwards it won't require to go through all those trial and error method. It can use that model for the references. Model based learning is the integral part of what you can say the reinforcement learning. So there are two type of models. Here you can that iterate the policy, we store and update the policy rather than doing this indirectly over the values. So we always store the optimal policy into the set and we go with this policy iteration algorithm for model based learning. So here pi is our pi dash or pi star. We can consider as our policy, optimal policy, which we are repeating, that we are adding the computing for the values of the pi and solving this linear equation which was seen Bellman's equation of the dynamic programming to repeat the policy. The next is what you can say going to see in next video is a deep learning. Deep learning is a type of machine learning where you are having a layer of different, what you can say, a depth in-depth data analysis. It's not something that you are trying to find out some very core meaning. Only the neural networks are used there. Let's see that in the next lecture. So for this, if you like this video, don't forget to subscribe to TutorASRumale. Click on the bell icon for the notifications, and ask your friends to subscribe to TutorASRumale. And thank you very much.